Okay, we are on to the theoretical part of today's lecture, where I give the definition for what it means to be a group. So I need to be using very generic language because there's lots of things that are groups and have this kind of structure. So if my main goal is saying what are all forms of addition, what are all forms of multiplication, how do they follow the same rules, and what can I expect of them, then I'm going to use a slightly different symbol, right? I'm going to use an asterisk as my generic operation. So depending on the setting, maybe my asterisk is actually standing in place for a plus sign. Maybe my asterisk is standing in place for a multiplication dot. Ultimately, the idea here is I'm expecting these to follow the same sorts of rules. So this is the way that we define a group is in terms of 4 axioms. Anything that follows these rules is a group. And one of the strong things about group theory is that all groups are subject to certain results about their behavior. There's certain theorems that work on all possible groups, including the modular groups that we've already been using in this class, the modular arithmetic, I should say. So first off, a group consists of a set G and an operation which I'm calling asterisk. And together they have to follow 4 axioms. So remember that the set G is the collection of all the different elements in my group. My operation is going to be defined at the element level. So axiom number 1, rule number 1, GH, right, G asterisk H or G star H, has to be an element of the set G for every element G and H coming from the set. So my capital letters are sets, my lowercase letters are elements. If you think about integers, this is saying that the sum of 2 integers should still be in the set of all integers, yes. Or if you think about real numbers, the sum of 2 real numbers should still be in the set of real numbers, and so on. So my operation has to give me back an element of the same type that I started out with. The product of 2 functions is still a product. The sum of 2 rational numbers is still a rational number, and so on. Axiom number 2, once I know that G star H is an element of the group, axiom number 2 says that parentheses work. So now if I have any 3 elements of the group, I'll call them lowercase g, lowercase h, lowercase I. There's 2 different ways I could stick parentheses into this formula. Either I do h star I first, and then G star whatever that gives me, or I do G star H first and then hit it with I. Those should give me the same answer. So if I want to be doing arithmetic and algebra in this setting, I need to know that I can group terms in a convenient way, and that won't disrupt my answer. So that's half of the axioms already. We're halfway done. The remaining 2 axioms have to do with cancellation. So axiom number 3 says there's a special element, and I'll call it E, and E has the property that E star G and G star E is equal to G, which I see I have left off of this slide. So there would be like an equal sign and then a G. I'll make sure to put that in the final version of these notes on the website. So if you're imagining that my asterisk actually stands for a plus sign, this E is actually the number 0, right? 0 plus G equals G plus 0 equals G. We call 0 the identity element. Or if my asterisk is your times sign, then my E actually has to be standing for the number 1. 1 times G equals G times 1 equals G. The reason why I've assigned it a letter name instead is so I can keep this generic statement, because again, I don't know exactly what operation my star is. The reason why it's the letter E, I think, comes from German, from the word eigen, but don't worry about that too much. This is just a standard way of presenting this axiom. So something in this group has to behave like 0 does for addition, or it has to behave like 1 does for multiplication. But that's really the same kind of behavior once you are thinking about it as both of those are kinds of group operations. Once we have an identity element defined, we can talk about axiom 4. So every element of the group, I'll call it lowercase g, has some inverse. Now, I'm not able to be use case agnostic here, so I'll just use exponent notation. I'll call this inverse g superscript -1. And this inverse also has to be in the set capital G. How do I know that the inverse is special? G star G inverse equals G inverse star G. Both of those will get me back to the identity element from axiom 3. So if you're working with addition, everything has a negative number where you add them together and you get 0. If you're working with multiplication, everything has a reciprocal where you multiply them together and you get 1. That's the same kind of behavior. We're just squinting a bit so we can't tell whether this is a plus symbol or a times symbol. Now, that is a very high-level, abstractified way of thinking about groups. And I recommend that we try to stay focused on particular examples that we've already been using in this course. So the big 2 examples for us, if we're thinking about addition, then the integers mod n form a group with addition as the operation, right? Any 2 residues mod n, I can add them together, I'll get a third residue mod n. The identity element is 0, and I can find my inverses by just doing negation, right? The inverse of A is minus A. Add them together and I get 0 mod n. Multiplication was a little bit trickier for us. We had to use a smaller set that I have been calling the units mod n. So the set name for this is Z mod n Z cross, or Z mod n Z times, take your pick. These were the residues that are relatively prime to n. And we saw that all of those do have multiplicative inverses, right? So these were the special residues that I can find multiplicative inverses for. The identity element is going to be 1, and of course the operation is going to be multiplication. A key thing to point out here is that in general Z mod nz does not form a group under multiplication. We do have to throw out some of those residues. That was part of the reason why our applications required us to get rid of certain residues before we could actually do cryptography. Now, there's one last rule that's very intuitive, but I left out of the definition of a group because it's not in the definition of a group. You may very well expect that when you're working in a group capital G, no matter what the operation is, that G star H and H star G are the same thing, right? Makes sense. A third plus a half is the same as a half plus a third. A third times a half is the same as a half times a third. If that is the case for one of these groups, then it gets a special label, and we'll call G an abelian group. Or sometimes you'll hear people talk about this as a commutative group. Abelian is named after a mathematician, Abel. So most of the groups that we've seen since grade school even, right? Fractions, real numbers, functions, those are abelian. The order that we do our operation in doesn't matter. It's just the nature of math education that we focus on the abelian groups. They are the most applicable to real life scenarios, and they are very nice to solve problems in. In our upcoming lectures this week, we're going to find out that not all groups are abelian. So there are, in fact, systems of algebra where the order that you do multiplication in matters. So again, if you've taken linear algebra, you already know this. The order of multiplication is a very important thing when you're multiplying matrices. A times B may very well be a different matrix than B times A. Or if you've seen cross products, you know that I times J, I cross J, is actually a different vector from J cross I. So while we are working in this space, we're going to explore some of these groups where the order that we perform addition or multiplication does change the result that we get. But at this point, I think we have been abstract enough for one day. I'll leave that for a future lecture. If this is still a little bit hard to grasp, try sitting down with one of the sets of residues that we've been working in this class. Take your pick, right? You can look at the integers mod n and try to see how the four group axioms show up where my capital G is my set of residues, my operation is just plus, and these formulas will work for residues mod n. You can also try this for the group of units, which is a phrase I might have dropped in previous weeks. It should make a little bit more sense now. That if my star here is standing for multiplication, and I'm only looking at residues relatively prime to n, then my identity element is just 1 mod n, and those were exactly the residues I picked, which have inverses. So I will get back to you on Thursday with some more examples of cool and interesting groups. See you then.